All right, everyone. I think I should be audible by now. Let's start. So, yesterday in the previous stream, basically, we got textures working. So, this is the current state of the system, right? We have colors and we have the textures. Now, for people who are using this at a high resolution and who are not completely marred by YouTube compression, you'll notice that this system actually has a little bit of this wiggle that's happening. We can come a bit closer with the camera. Currently, this is all static, as in the camera is manually set up inside the code, and so I have to recompile every time I change the camera's location. Not the perfect thing, but we'll get there over time. So camera position, we'll set it to -2. That should be enough. Run it. Right? So now you cannot really see it, but if you look at the far end, you would see a little bit of this shimmer that occurs. All right. So here, this problem generally occurs due to what is known as mipmapping. I'm not certain if this particular instance of this issue is happening because of mipmapping or not, but we anyway have to implement mipmapping for filtering for things that are longer and further away from us. So might as well try it out. And in order to actually try it, we will make two versions, two copies of the same thing. All right. One of them will be mip-mapped, the other one will not. And in order to, do this sort of an experiment, currently in the current state of the rendering system, we will need to, let's say, have a bit of a fancy setup. But we'll get there, right? First things first, we need to duplicate the location. And currently we're using model matrix as a part of camera data itself, right? Camera data here has the model matrix in it, which means at a time there can only be one model orientation in the system. That's not right. That is not how things should work. So we remove it from the model system again. And we'll add it around here. Wait, why is it not working? Control X and Control V. Yeah. So we'll add model matrix here. We'll figure it out if it needs to move around from here or not, but for now we'll just make that move. And yeah, since we did the change in C++, we need to make the change in the shader code. So model goes away from here. If model goes away from here, there's no way we can get the model here, right? I'll do a little thing here. So this is a uniform plot 4x for model. Okay. Don't ask me what this is exactly. So actually do ask me. So this is a uniform parameter that we're asking as an input to the input, to the function input, actually as a function input. This is a part of slang. This gets converted into what is known as a push constant. There is an alternative where we can add it outside, and we can do that by saying the same thing, uniform float 4x4 model, and we can then add an attribute that says vk push constant, and that will essentially mark the model as a push constant, and we can use it here. And we can even use it in the fragment shader if we mark it here. But we can try both sides. It will be roughly similar to each other. We'll see the differences as well. Sang is a unique way of handling things. It's not exactly a core part of the problem. Model matrix gets moved differently. So we will also move it away from the rest of it. Right now, we don't have a concept of world. We don't have a concept of game objects or entities. So everything is just haphazardly strewn about. But we will start collapsing this API soon. Now, once we have the model matrix, we want a second model matrix. So model matrix 0, model matrix 1. And we'll also rename the original model matrices. So you can just go to camera data and look at this model matrix, and model matrix 0 and model matrix 1. Can this be an array? Yes. Am I making this an array? No. Why not? Good question. So array it is. Okay. Go back to the model matrix. Nope, that's the shader code. Missed it at H. Yeah. Make this an array. So remove that, remove this, std array xm. Get ready for a big shift in the formatting just due to one single change. And we build solution. Okay, model matrix is not a part of missed data, camera data. That is entirely fair. Model matrix is completely a part of the list itself. And this is an array. So we'll remove that for auto and model matrix. That's the model matrix, specific model matrix we're looking at. We've taken it out as DirectX XM matrix, taken it out as a reference. So we can modify it here. Model matrix becomes again the model. All right. We can even, do a proper thing, a connect transform, because that's what it is. It's a transform. Right. Oops. So, there we go. That should rotate both of these matrices just fine. We don't actually need to mem copy anymore because the rest of the camera data doesn't change. Okay. And we get down all the way to where we put the data onto the system. So this draw. Before this, we will just say vk command push constants. So push constants are effectively small pieces of data. I think it's up to 128 bytes, not kilobytes, 128 bytes that you can write directly into the command buffer. So this data will be copied into the command buffer, sent to the GPU through the command buffer when it's executing on the driver, and directly used by the GPU. So you don't have to make specific separate memory data for this, memory location for this. Requires a pipeline layout, which is list.pipeline layout. Requires shader stage flags. So since we made it a global thing, the shader stage flag will be shaders all graphics. All right. And offset would be 0. Size would be size of model matrix misc, not model matrix, 0. It's the same size for both of them. And the values will be misc dot model matrix 0. Okay. So what we've done is we've pushed one constant. Now this will be incorrect. This is absolutely invalid because the pipeline layout never actually initialized. So never actually told the system that, hey, we need a certain amount of push constants. So while we told that, hey, we need descriptive sets, so it's here. We said that we have one descriptor set layout, and it knows that it has to create those slots for the descriptor sets. It doesn't know that it has to create slots for push constants. So we have to add manually a push constant range. So we get push constant range, push constant range. Always very explicit with the names. VK stage flags is pipeline stage, no shader stage. So VK shader stage all graphics. Offset is 0. Size is size of DirectX XML or XM matrix. Oops. All right, so that's push constant range, and we only have to provide one of it. So one push constant range goes in. That's it. This should generally just work. We'll see. There's a level with the create graphics pipeline. All right, what's your problem? I've made sure the configurator is on, so we can see the errors. In a source variable, it's again the shader corresponding descriptor set must be laid out to match. Which one is this? Perform texture. is restricted to set 1. So here we should be using, ideally we should be using reflection inside the shader slang. Right now I'm just doing guessing. Right? I'm just using guess mode. But in reality, I should be using proper systematic reflection data, or I should be hard coding the set numbers and everything. We can do that. We can make it hard coded set numbers. But for now, it should be fine. This seems to have an issue. It's going to set, so it's set 1 binding 0 variable per frame data, is set 1 for some reason. Well, it should be set 0 because this is a uniform. Sorry, this is not a uniform, the push constant. Perhaps the double. Able solution, we'll see. One by one, one step by one step. Nope, that's still an issue. So for some reason, this model seems to be pushing out the uniform location. Can't figure out why. But let's take it as struct per installs data. For now, we're putting this as part of the code itself here. I call it transform, as we've come to call it in the main. Uniform constant buffer. I think the lack of a constant buffer was the one throwing it out. Per frame, but per instance data. And we can call it PCB. All right. So here is the PCB transformed. All right, let's try this out. Is that the issue? Was that the issue? The SDL3, of course. Label solution. Right. So now it works. And the model is no longer passed as a part of the camera data anymore. So that is cleaner, really. Okay. Now let's do a little thing. Okay. One small thing, which is we move the matrix to a side. So we don't keep it in one place. Hello. Sorry if you were sad yesterday. Ah, please. You should use whatever you like. There's nothing wrong with using SDL and OpenGL. In fact, if you want to learn graphics, that's the way to go. For to learn game dev, I would suggest Raylib. But these are suggestions, right? At the end of the day, you are the one creating your thing. You're the chef. Decide. Well, I'm not as eloquent as Chef John, so I can't come up with nice rhymes. Feel free to use what you like. Just make sure that you stick to it, right? Be consistent. Don't do a little bit of Raylib and then a little bit of this and a little bit of that. Stick to one thing, do it properly, do a small project, then move to a next thing, right? Learn one thing at one time. That's all. Take your time to decide. There's pros and cons in both sides. It's really your choice. Okay. So, coming back to this, where were we? Yes, we put the push constants here and things were okay. We will go back to list data init, where we initialize both the model matrices. Now we're going to see the test of, let's call it linear algebra of mine. I think this might be wrong, mostly because of like my understandings of the API, but we'll see. So DirectX, translate, I think it'll be XM, translate, matrix, translation, there we go. That's our translation matrix. Oh, they're automatically created for us, so no problem. X is 0. Make it X 1.0, Y 0.0, Z 0.0. Okay, so it's 1 in the x-axis direction. This one is -1 in the x-axis direction. I'll correct the function name in a second. And this becomes XM matrix translation. So let's see if it moves to the right. It should move to the right. Okay, here's what has happened. So the rotation is still from the origin. It always is from the origin. So the order of operations for creating a matrix like this is always to first translate. No, wait. First rotate, then translate. Okay. And scaling before that. Because we always want to do things with respect to origin. The origin at the start is at the center of this particular rectangle because the way we made it, it's -1 comma -1 up to +1 comma +1. So the origin 0 comma 0 is at the exact center of this. If we first move it by 1 unit, which is what we did, then we rotate it. It will rotate across the new origin. So after translation, it becomes -1 comma -1 to 0 comma -1, and +1 comma +1 becomes 2 comma 1. So that is the issue. My translation is not going to work properly. So I'm just checking the comment. Thanks. By the way, any ideas what will match my studies? Okay. So in that case, I would say if you're learning C++, you don't have much experience with it already. I do not recommend using OpenGL because OpenGL means you will be learning graphics, right? You should focus on learning one thing at a time. So either learn graphics or learn C++, and you can't do graphics without C++. At least you can't do graphics in C++ without C++. So learn C++ first. And in that case, I would suggest not even using SDL or Raylib until you first understand C++. Okay. And then start, like, as you learn new concepts, start using something like Raylib or just SDL, plain SDL without the graphics part, and just do 2D stuff. Okay. Coming back to this, we need to rotate and then translate. The issue with that is that means the model matrix thing here has changed. So we'll actually create a new struct, and in fact, let's just make it outside. So struct transform is a directx xm float full. It contains a position. It will contain xm quaternion. No, it's I think float 4 itself. Quaternion, so that's rotation. Then we'll do small hack. That's a float 3. This will be just a plain old float. Yeah, okay. Float, which is rotation. Oh, sorry, scale. So what we'll do is we'll just say there's uniform scaling only. That compresses the data a little bit. Non-uniform scaling is not very common, so we're just gonna keep it like this for now. And instead of being a model matrix, this will be model transforms. So this becomes transform. This becomes model transform. Okay. And that requires us some work here. Model transform. Transform. And this also changes. So model transform 0 dot position equals xm matrix translation become xm float 4, float 3 actually. Rotation, so rotation xm rotation quaternion rotation axis. Yeah. So quaternion rotation axis, and it will take. This is interesting. So it takes an fxm vector, but it gives out an xm vector only. So this has to be an xm vector. Similarly, this I'll change it to xm vector as well. XM vector. I think that was sample set vector. Set. Yeah. So it takes each of these components to create an XM vector. The other option is to use fxm vectors. So fxm vectors allow you to create That would be fxm vector. It's okay. Vector set is fine. We don't need it to be an fxm vector. All right. So coming back, quaternion rotation axis, it needs an fxm vector as an axis. So fxm vector dot vector set, I think. Yeah. xm vector set. That's a rotation axis. So 0.0 because it's not a complete thing. And the rotation for this will be 0, 0. Like angle we're using is 0, 0. So we don't care. That will work itself out. Similarly, oh yeah, this can actually use XM float 4, which we can directly create. And this can get assigned to it, I think. It does not. Oh my. Or it takes an XM. Anyway. Doesn't matters. Dot not matters. Sorry. And scale. So scale has to be set. It doesn't default correctly for us. So scale is 1.0 because default is 0.0 and that would mean we can't see the thing. We just copy this. So paste twice. Change matrix 0 to matrix 1s. And vector set here becomes -1. So that should be enough. It won't work on the main side because transform is not complete. 12 bytes added after scale for position. My. That's no good. Because XM vector is not float 3. So it doesn't give us much benefit on the scaling. The scale thing. Too bad. Okay. So node 3 it is. It should be fine normally. So for now we wouldn't care too much. We use 3 instead of 4. That's it. Done. Same with this. 3 instead of 4. That handles itself. All right. Build it. And that failed again. Let's see. Okay, first model matrix is not a part of this thing. That's fair because it's model transforms, right? Similarly, this instead is a transform ampersand. Cannot do matrix multiply directly. That has to be fixed again. So here I would say transform dot rotation equals DirectX XM quaternion rotation that wasn't it. Quaternion axis I will also not it. Okay, let's just do this. So make the axis vertical. That will be the y-axis. DirectX fxm vector. Actually, fx set xm vectors set. So y-axis, so 0 on the x side, 1 on the y side, 0 on the x side. 0 on the W side, so it's pointing up. The angle is, I think we were using 60 degrees per second. We can try that. We have to go to radians, so DirectX again, convert radians, 60. So it takes 60 degrees, converts it to radians, and multiply it by the time. That's delta time dot static cost at the time as a float. Okay, so that should rotate the quaternion, specifically just the quaternion for these things in the matrix. So those will handle themselves. Here we will construct the final matrix. So that is handled using a lot of work here. DirectX translation from vector. That takes the model, that takes misc dot model matrix or transform 0 dot position. So it takes the position, so float 3. Okay, so this is like a general rendering engine, but it's not going to be very generic. I will use it for making something simple as an experiment, and I'll keep modifying as required, right? So I'm not committing to either side, let's say. One second. Okay. So vector 3, it's not happy with vector 3. Needs to convert it to something like vector 4, I suppose. So DirectX, what's some vector F32. That's the union between float 4 and XM vector. So XM vector, so float 4. Unfortunately, it doesn't have a version where it can take a 3-dimensional position. So what we will do is we will extract the position into X, Y, Z. And we'll provide the position here. In fact, we don't even need that anymore because we don't need a vector. So XM matrix translation, that creates a translation matrix. First thing we have to do is not translation. So the first thing that we have to do has to be added on the right hand side. All the multiplication happens such that you take a vector and then you multiply the matrix from the left side. So translation is the last thing that will apply. The one thing before that is XM matrix from quaternion, rotation quaternion. There we take misc dot model transform 0 dot rotation, that gets the quaternion and it will handle itself. Last is scaling. So DirectX XM matrix scaling, scale X, Y, and Z. It just takes misc dot model transform dot. It doesn't take this. Instead, it takes model transform 0 dot scale, and it simply copies this 3 times, right? I'm just going to simplify it by writing scale here. I'm just saying scale, scale, scale inside scaling. We're not using scaling right now. So to be fair, this is not entirely necessary, but it's best to have it. DirectX XM matrix transform equals that. So normally in a normal engine, this will happen as a part of converting local transforms into global transforms, which is effectively what we're doing here. And I'll also simplify this particular task for us by hoisting transform out. Okay. Well, that handles itself a bit. Interesting. And now we should be able to change this to size of transform and data of transform. Okay. Let's check this out. Okay, what's happening with this? So the main issue, if I'm not wrong, is rotation not applying properly. So rotation here takes the rotation from model transformation and does it. Model transformation rotation. This is misc data. No, this is place transform. So model transformation rotation must be happening up here. The axis, y-axis is up. Hold on. Did I make a mistake in misdata? Quaternion rotation axis is x instead of y. Well, that makes much of a difference with the angle, but better to have it correct. If I'm not wrong, I saw it flip at the start. So what is happening? Creates a quaternion. Rotation equals rotation axis times. Oh, so it just takes the 60 times delta time because we never multiplied this with the original quaternion. I'm not very strong with quaternion maths, but multiplying quaternions. I don't remember if it is multiplying or addition that you need to do. Yeah, combines the rotations. So wasn't wrong. DirectX, XM, quaternion multiplication. You take quaternion 1, you multiply it with the old quaternion that we had, so rotation, and we close it. Let's see if this works. Fine. Run it. That's not right. It does the exact same thing it initially did. Something is wrong with the ordering. So we did translation, rotation, and scaling. Was this our order wrong? So this is definitely wrong, but one can try with this. Okay, this is the intended behavior. That's what we're looking for. So why is it that TRS, translation, rotation, scaling matrix, is in reverse direction? That has to do with DirectX math, and sure. DirectX math, multi TRS matrix. Let's just search for TRS matrix. Polling line, Cindy. Very near there. Goodbye. So, okay, what's the thing that's happening here then? Let's look at discussions. Do some details. Should always be 16 byte aligned. Hmm. Projection world view. Eve. Cancellation. Row region matrices. DirectX uses left-handed coordinate systems with row major matrices. HLSLC is default to consuming column major matrices. That's DirectX, but yeah, I'll get this connected, like properly, consistently connected, probably offline, because it's mostly plumbing. But once I do it, I'll make sure to take a note of it. Okay. Now, let's run it. Should be one offset. Okay, it's fine. Let's look at the transform that we created. Let's first draw two of them. So we can easily draw two of them by doing this. Everything else is constant, like nothing else has changed. All we do is we say for, we say transform and transform, model transform, model, but like local transform because it is a local transform. And we take this model transform, right? Then here, instead of this thing, it will be world transform. And we just have to set the world transforms in here. Similarly, model transform 0 becomes world transform. Again, no, sorry, local transform. Again, and again. All this becomes again world transform. And so what we're doing is we're just running the same thing twice with two different translation matrices. And so as you can see, you get two different objects with different positions because we started them both at different initial positions. We can even make them go off, like out of phase by creating the initial rotation matrix a little differently. So here we can say this is 60 degrees. The angle should be in radians. So convert XM convert to radians and you give it 60. Right. Build, run it. So now they're offset in phase. Cool. Let's look at Mipmapping now. I have delete long enough. So what does Mipmapping mean? It means you create progressively smaller copies that are pre-filtered for each of like the level of details, right? Something that is close to you on the screen, you use full resolution. As it goes further away, you use lower and lower resolutions of it. The best part is because it scales effectively by 1/4 every time. Since, you scale it half on height and half on width, it's 1/4 the size. The summation ends up with less, it ends up requiring less than 50% extra memory. All right. So let's start. Actually, if my math isn't wrong, never mind. Let's start. So we go to where we created our image, we uploaded it because we use a command block for that. So image upload. I will just search staging. No, texture, sorry. Texture. That's the view. That's the texture, sorry. That's the texture, right? So how many MIP levels do we have in texture? The answer is 1. So that's what we standardly stuck to. Anyway, we only have 1 of them. So what we are going to do here is we're going to calculate how many MIP levels we actually need. And in order to calculate that, we need to take logs. How many MIP levels do we need? Whenever we end up with a single pixel left, that's how many MIP levels we need. So for a 512 by 512 picture, we will have one more MIP at 256 by 256, one more MIP at 64 by 64, sorry, 128 by 128, one more MIP at 64 by 64, 32 by 32, 16 by 16, 8 by 8, 4 by 4, and so on, right? Each power of 2 until 512 gets 1, which means it goes from all the way to 0, all the way, sorry, it goes from 0 all the way to 2 to the power 9. That's 512. That's 10 total MIPs. And thus the calculation goes like this. You get the width and the height. So that's where we have it. Now we calculate MIPS. So calculate MIPS. We say log. Std log. Yeah. So there's log 2. Quite useful. There's log 2f. I think that's good enough for us. So log to the base 2 of the max. This will be max of width and height. Okay. So if we have an image which is 512 by 256, then the next MIP will be 256 by 256 by 128, and keep reducing like this until it comes down to 2, 1. After 2, 1, is there a point in going to 1, 1? And generally the answer is not much, but 1, 1 is hardly any amount of data for us. So we don't particularly care, right? So we just do the MIPS using the max. We can do it with the min if you like, but then the last one is a little stuck. So anyway, we can check how it works online. How many MIP levels for image. So yeah, see, max. Width, height, depth, but in this case, we know the depth is 1. So it's just width, height. Anyway, so once we get the log of this, the log can be in fractions because we might not have an, as they call it, pen pot, log power of 2. So we may not have a non-power of 2. And so we may have a non-power of 2. In this case, the log will not end with a whole number. It will end up with some fraction. And we want to use, we can either use the ceiling or the floor, right? Problem with using ceiling is it means we will use more MIPS than we actually need, right? Like for example, how many MIPS does 3 need? 3, then it's next is 1 directly. It's not 2. It's directly 1. So it needs the same number of MIPS as 2. So they are, the better thing to do is to floor. We do floor. Again, floor F because we're using the floating point functions. And once we've done with the floor F, it should be an int cast. So int, it will ask me to do a static cast, and that's done. It obviously is uint32t, and that becomes MIP levels. So uint32t, or in this case, I can say auto because we know what the type is. Auto MIP levels equals that. And now I can say MIP levels. Okay. So that is generated, like that will be created, but this still will not be returned to, because when we wrote to the data, we wrote only with specific MIP levels and everything. So once the image resource was created, we have to look at the view. Again, image count, level count is 1, layer count is 1, but here we should have level count as MIP levels because the image view will consider all the MIP levels, and that will just work. We don't care about this. Width is linear. That was fine. So far, so good. Okay, here. So once we're done with the staging, we copy the data into the staging buffer and then we transfer. So I should actually comment here. So this is staging to texture transport, right? This happens, all of this happens, and we're done here, but we only copy everything to one specific MIP level, the MIP level 0. We did not copy anywhere else. We only copied to MIP level 0. MIP level 1 means manual initialization, but we're not going to just copy the data because that would not be correct. The data size is much larger. What we want to do is scale down the data and copy it there. Scaling down, again, is not something we can do trivially, let's say. We will have to put commands. So just like we did copy buffer to image, we will have additional commands for each MIP level that further reduce the size and keep pasting it again. So how do we do that? Transfer to ready dependency. First, we will go to image subresource layers here. We're not subresource layers. That's for copy. We're in the dependency where we use subresource range, right? These subresource ranges, if again checking, is everything, right? It's all the MIP levels. So that is okay. We now need a set of barriers which only handle MIP mapping. So creation to transfer dependency, then on each MIP level. So going from full resolution to half resolution, there will be one memory barrier which converts the original one to a transfer source, and it converts the next level to a transfer destination. Okay. But in this case, since we already have everything as transfer destination, we don't care, right? So right now the entire image is transfer destination. Optimal. We will only swap. Sorry, this is not the right one. This is transfer to ready. Creation to transfer. So this is transfer destination optimal. We will only swap the first image, right? Full resolution image to transfer destination source. So we need to create a custom command. So custom subresource, which is single MIP subresource, let's call it. So creation to transfer barrier, there's a file, dependency, there's a file. Now here I'll say vk subresource range, cost. No, it won't be cost because we need to change this. MIP level sub resource. Designated initialization, aspect mask. Hold on. Yeah, aspect mask, vk aspect color, because we're looking at colors. Base MIP level. We start with 0 for now, so we're going to leave it like that. Level count will be 1. Base array layer will be 0 and layer count will be 1. We're only looking at single layers, right? So this is MIP level subresource. We're fine with this. Next would be the barriers and the dependency. We're going to copy that and paste it here first. Now this becomes next prepare next MIP level image barrier. I know that's a bit mouthy, but it's better to have them very easy to read. So this goes from transfer destination optimal to transfer source optimal. Okay. Each of these levels independently get converted into transfer source optimal. And instead of taking the entire subresource range, it will take MIP level subresource range. Okay. That makes it the barrier. This is fine. Images texture, that doesn't change at any point of time. All right. So far, so good. This dependency needs to take the MIP level image barrier as the memory barrier. And then we need to use it. So where do we use it? Each MIP level. When does each MIP level happen? So between this, so this is start. So this is start. This is end. This is first. So staging to image L0. And now we do MIPs. So MIP mapping. And now here first, what we have to do is, this one is outside, which is vk pipeline pipe line barrier to command buffer. And this one will be prepare next mid level dependency. Okay, this is fine. Then for the prepare mid level image barrier, we'll take the sub resource, the base array layer, and we'll increase it by 1. Okay, I think one of these is constant somewhere, which is issue, this one, right? So yeah, 1 second. So this can be constant. This can be constant. It is only copied in here, but this has to be kept updated every frame, every mid level. So that we'll have to do. Now for int I equals 0, I less than mid levels, plus I. So this will handle each mid level. And what we can also do is, instead of base array layer being ++, we can just set it to mid levels. Okay. Now we want to make this pipeline barrier at the end of each MIP. And the reason I do this is because that means the last MIP level that gets assigned to also gets converted into transfer source. And this final transfer to ready dependency can start using that source instead of using one of them as a different layout than others, because that can be a little, let's say, confusing. So transfer to ready dependency, transfer destination becomes transfer source optimal. Sorry, SRC. Yeah. Now, coming back to MIP levels, we'll do this. We'll just copy paste it here. Each base array layer keeps increasing, and so we don't have any issues with it. Right? We will add, where, as I said, we can also do it like this. Leave it up here. I would say this is equal to I, which is much more reliable. And then you can change I to be more informative as well. So mid current right mid index. Current right MIP index is less than mid levels. That was fine. Current right MIP index, current right MIP index, right? So now what happens is we need to copy again, but copy is 1:1. It can only take from one size to another size. What we need to do here is known as blit, which allows us to change the, what do you call them? Size as well. It allows you to scale things. I'm going to use blit image info 2. Blit info. Because CMD is actually frame in use.command buffer. Blit info 2, because that allows me to just write everything once. Blit info 2, blit info. Create everything. So we can structure type blit image info. Next is null. Source image is texture. Texture. Source image layout is transfer source optimal. So we can image layout transfer source optimal. Destination image is also texture. Layout is VK image layout transfer destination optimal. Region count is 1 single region. UK filter linear. We're going to use linear filter here. P regions. So the regions are VK image blit 2, VK image blit 2, image blit. Type is VK image blit in. Image blit 2. P next is null. Source sub resource, right? So source sub resource here is image single image sub resources for mid level sub resource there. Source offset. This is a 3-dimensional offset. Yes. Takes 2 offsets. That's interesting. 0, comma 0, comma 0. That's one of them. And what we'll do is we'll look for the spec to figure out what the other one is. Cool. Source offsets is an array. Bound of the image is in bounds within the source subresource. So that goes from this until, does this work? Let's see. It does work. That's interesting. Depth is 1. That is rather interesting. But I shall not use it. It seems unclear what's happening in there. Destination source, again, mid-level subresource, and these are incorrect right now, and we'll have to fix it, but we'll get to that. 0, comma, width, height, allow, yeah. Everything, most of the data here is incorrect. Why is it talking about aspect flags? Oh, subresource layers, of course. Right? This takes subresource layers. This is more accurate. Makes more sense. VK, aspect, color bit, width level is 0, base array layer is 0, layer count is 1. We can copy that because this is going to be roughly the same throughout the process. We will be editing it over time, but inside the rest of the code. So VK, image, layer, subresource layers, const. So resource layers, lip. To be fair, it's the exact same subresource layers as before, but it's better to rewrite it. Like, it's simply better to rewrite it because it is clearer for us to follow later what the logic is. Yep, that's incorrect. Aspect mask, spec color bit, width level is 0. That will keep changing, but since this is just a template of the original one, we don't care. Base array layer is 0 and layer count is 1, right? So mid level subresource, so mid subresource layers, mid subresource, mid subresource layers. Max offsets is having an issue. What's the problem? Width becomes, wants to go from uint to int. Static cost, that shouldn't be it. It's actually the other way around. Yeah. Cost int 32t. Okay. And destination offsets. To be fair, I can skip this, like this whole thing here, because we'll have to keep rewriting it every frame anyway. But it's better to be correct with it. So I'm going to write it here. Static cost int 32t width by 2. The reason we're using by 2 here is because the next MIP level will be half the size of the original MIP level. And this will keep happening. Like every layer, we're going to half the width and the height. Okay? The source offset, so the starting point, will be the same. Destination, the origin of this particular rectangle will be the same no matter what, but the size, so the other corner, will keep changing, and each time the source offset will be double the size of the destination offset, or more like destination offset will be half the size of source object. So while I've said that it's MIP layer subresource here, the MIP level of this subresource will be different. So image blit dot destination subresource dot MIP level equals 1. And really, I'll write it for the source as well, just to make sure that it's very obvious later on that this is happening. All right? What's the problem here? Cost expression. Why? Okay. Now, moving on, what is the next thing? So after region count, it takes one region. The region is blit. Image blit is there, so it takes image blit. Takes it as a pointer, so we can keep modifying the same image blit from new blit info mutations, let's say. Yeah, that should handle itself. Continuing. So prepare next barrier. This one is a blit info. So the first blit info we do, right? The very first one, it will be copying from the source, which is the entire width and height, to the half width and height. Now, what I'll do here is because I have to write this every time, and because I will keep halving it, but I don't want to modify the width, the actual original width, I will create mip width as a separate thing. Okay. So int 32t mip source width equals width static cost, and it will handle itself. Int 32t mip source height close again static cost int 32t height. This becomes width, mid source width. That becomes mid source height. Okay. And we'll also make destination width and destination height a thing. Dest width, dest height. Because this is actually a clamped value. So here, width will be divided by 2, height will be divided by 2, and we will do a max. STD max between that and 1. Why? Because we don't want a MIP size of 0, right? After 1, the halving is always 0. We don't want it to be zeroed out because it doesn't make sense for an image to be of size 0. Cool. And with that done, MIP source height is fine, and this becomes MIP test height. Similarly, this becomes MIP test width. Okay. Now again, I will manually rewrite it here, because that allows me to keep a little bit of consistency. So source offset 1 dot x equals MIP source width dot y equals MIP source height. Paste twice again. This becomes test, 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 and test. Okay. So why do I do this? Because I will be doing this every frame. This is the modification that will occur every single frame. So I keep it as a consistent available thing that I can keep doing, right? So I just copy that. So on each frame, I first do the blit. For the first frame, this is ready. This is completely correct. And now I have to write to the next set of things. So image blit becomes, if you're taking a MIP level or just a MIP level, you take current right MIP index. You take the next right MIP index. So that's current right MIP index plus 1. You take the source offset x, which was source width, which now is destination width. Source height, which is now the destination height. And similarly, actually, we'll correct this. So we do the calculation here, which is MIP source width equals MIP test width. MIP source height equals MIP test height. Source height becomes MIP test height. MIP Dest width becomes mip source width. So this thing we did up there, right? Here, I'll change it to mip source width again. Again, consistency is key. Mip source height. The casts become redundant, so remove them. Remove dynamic cast. Copy this. Really just paste it here. Okay. That should handle most of this. Finally, transfer. I'm writing this also to format it. So transfer current lip level lip current lip level as source. Alright, done. We need to remove that. Alright. What next? So once all of this has been set, it should automatically, work out. Not automatically, but like we've set up most of the things correctly, seemingly. We have to look. Okay, what's wrong? Argument cannot change from const ty. Max is a float. Max isn't written a float, but it just needs a float. It's a warning. That's an error. So mip levels is not constant. Inventory to mip levels is not a constant, so this cannot be a const expression. Not succeeded. Anyway, there is an error here. We do not want this, so we will fix it. So here I would say max. Let the max be the integer max, and we do a static cast of float, right? That should handle itself. Build. Still an error. I'll check by comparison on this line. Feeds call on this line. I'll leave it for now. We'll see it later. Okay. So, is there an issue? There is lots of issues. So what it says is there is no new layout as transfer source optimal is not compatible with the image, with the usage flash being transfer destination bit and usage sample bit. That makes sense because when we created it, we did not say that the image might be used as a source. It's a pure destination image. Now, some people can optimize this for some systems where you can do a source and destination on one image, do the mip mapping, and then just do a transfer to another image. But no point really doing that, at least for now. So here, we did a transfer destination. We also need to do the image uses transfer src that. And build. So we run it. But yeah, still errors of plenty. We'll look at them one by one. First, read after write hazard detected. We keep command plate image reads when synchronously being written to. This makes sense because we did not manipulate the pipeline barriers properly. So that one is next. Yeah, this one. So we only change the layouts. We also need to change the masks. So this says fragment shader bit, but in reality, we are just copying, right? And this is also copy. In fact, it's not even just copy, it's a blit. There's a specific type of it. It's called BLIT, blit bit, see? Both of these are blit. So both source and destination are blinked. Here it's a write bit. Here it's a read bit. I think there's a blit specific one as well. So blit. Okay, that's an access clause. So access to blit. Transfer write bit. Read bit. Yep. Is there more data to this? No, there's no. So now what happens is it says, okay, we're going to take from blit write to blit read. So it has to be ready. All the transformation, everything has to be done between the write of the previous one and the read of the next one. What are the next set of errors? The write after write hazard performs image layer transition on the image, which is previously written to by command copy buffer image. Layer transition does not conflict with the previous write, which is access transfer write bit at copy bit. Okay. Now what's happening? So this we said is specifically a blit. Okay. However, in the previous one, they did a transfer. So we will be a little more generic. We'll say transfer bit because transfer is more general. Blit and copy are both subsets of transfer. That should fix it, but let's see if it does out as well. Transfer write bit accesses at this thing must allow these accesses at blit bit. So image previously done access there. Access is at copy bit, but to prevent this has an equal access at blit bit. Okay, now what? So this blit, again, let's change it to transfer. It's not generally the problem. I don't think that is the problem, but synchronization can be a pain sometimes. Right bit accesses at copy bit, but it must allow it at blit. Again, same issue. Okay, let's not care about that for a second. Mostly accessed. Transition, which was read by image bit. Okay, hold on. There is one thing we haven't fixed either, which is conversion from the transfer to ready dependency. Here is a copy bit. It should be transfer write bit. Right? Takes from last transfer bit and goes to the fragment shell. Should solve one last error, but nothing more than that. Cannot transition from source optimal and the previous known as destination optimal. Aspect 1, level 1, layer 0. Layer 0 is fine. Aspect 1 is fine. Level 1 is mid level 1, which was a source previously. So is a destination previously, but it should have been a source. So why is that happening? Let's check it here. Run it. And the command link to let info says about P regions. So index is 1, that's fine. Mid level 0 gets copied into mid level 1. The size is also okay. It does so hit a linear. Profile validation is also okay. Next, validation will be screaming at us a bit. So we did a write after write hazard. command lit image writes to the image, yes, which was previously written during image layout transition initiated by command pipeline barrier 2. Okay, what does this mean? So the issue here is actually quite nice. That's fairly understandable now. Okay, so we only did a pipeline barrier up there, prepare next level of dependency, prepare pipeline barrier, where we convert from destination to source after the transfer has concluded, right? What we haven't done is for the destination. This is for the source. So prepare next MIP level source. And this is destination. These aren't done, right? So what does destination do? We'll fix this in a second. So what does destination do? So the source level does a transfer. So it does a layout from transfer destination optimal to transfer destination optimal, while the destination one doesn't care. So image layout undefined. I'm saying undefined, this would be a bug, but this is a feature. If both the layouts are the same, nothing happens. That's a part of the spec for VK image memory barrier 2. It was added in the second version of this particular API. Not Vulkan, but like this memory barrier stuff. Okay, stage mask. Transfer write, that's fine. Transfer read, this changes. So we are waiting for a transfer write again. Okay, this is in fact a blade write, and this will be exactly a blade write no matter what. We are waiting precisely for a blade. While the source of this is precisely a copy. We also know this because we start from copy every single time. All right. And now this next level next barrier and this first barrier, both of these need to become an array. Array of prepare next MIP level pairs. Barriers equals array. Shouldn't be doing that equal stuff. It's kind of a bad habit, I guess. I'm going to copy that, comment this, copy that, uncomment this. Cut. Cut also works quite nicely. This explains what exactly it was, right? So I'm going to leave those as comments. Okay. This was fairly expected. Not much to do about this. But we did solution and we see. Okay. Prepare next level image barrier is incomplete. That is fine because prepare next level image barriers dot size and prepare next level image barriers dot data. This should handle itself. Build. Prepare next level image barriers, sub resource range barrier. Okay. So 0. Should be base array linear is 0. No, base array linear is always 0. Where are we? This shouldn't be base array linear at all. This should be base MIP level. I think there's another bug there. Yeah, base MIP level. Where we come there? Base MIP level, and for the 1, it should be MIP level 1. Similarly here, prepare next level barrier 0 and 1. I can even just write like next MIP level index if we so want. Current is aim check, that is fine. Spectrum mitigation will figure it sometime. We don't care about that right now. Okay, much less in terms of the number of problems. Base MIP level 9 is greater than or equal to MIP level count of the image itself. That too is expected. I mean, not expected as in I thought about it, but expected as in, okay, that's an obvious error I can make. So this little thing is known as an off by one index error, very common for software devs. One index, because I do a +1 here for the next MIP level. The destination MIP level can be above or equal to MIP levels here. That shouldn't happen. So in fact, what I will do is I'll swap from a for to a while loop. Okay. This part in the while loop is, I think, fine. That part has to go. Never mind. Let's keep it to a for loop, but this part can be removed. We can look up there. So here we use the current MIP index. I can copy this. Current MIP index can be moved up here. Make this next MIP index. Next, right MIP index. And this is equal to current right MIP index +1. Okay. And now in the for loop, we can say next right MIP index less than this. This again can go away. This, as you can see, is coming down to becoming a while loop anyway. So next right MIP index equals current right MIP index +1. Current right MIP index equals next right MIP index. This is too early for it. This should happen after we've done all the writing. And now we can just make this next right MIP index. Next right MIP index, right? So far, so good. Moving on. So this for can be shifted to a while loop. It did it. Build solution. That is fine. Submit. Any errors? Yes, some errors. Can I transition from destination when one is source? Why is that? So this did not exist just now. So why is it happening? It worked. So what did I change and what did I do wrong in that change? Okay, base MIP level is current right MIP index. Oof, there's a small bug. Small bug in this that I need to fix. I need to undo all of that. All the way until the while loop. Okay, so here's the bug. This is a current right MIP index. So that should start with 1. Okay, that's not the source, that's the destination. I'm going to even rewrite this to destination MIP index. Yeah, call it MIP index, right? It's supposed to be MIP level, so okay, let's be correct. Okay, so destination MIP level. So this MIP level here is the transfer we'll be doing, is a blit we will doing next term. So this thread for next iteration. Okay, so this is the next step. So in the next step, the destination MIP level will be increased by 1. Okay, and this is fine. This is also fine. Destination MIP level should be less than 1. That too is proper. The problem is here, if the destination MIP level becomes equal, this is equal, this is equal plus, sorry, this is 1 less than MIP levels. When this is 1 less than MIP levels, this is equal to MIP levels. And that's fine. So the next time destination MIP level gets there, hold on. Push invariants. Okay, MIP level is 9. This is 8. What is happening? So this is 8 that succeeded. If this is 8 now, then the previous time this was 7, this was 8. So this should be fine. Okay, now we can look at this. Base MIP level is greater than the MIP level image count. Base MIP level plus level count was 10, which is greater than the MIP level count. So, okay, we're off by 1, then why are we off by 1? So MIP level equals 1. We start that, do that. Tuition MIP level is. So image blit. This is the direct thing we use. No. Image blit is here. We use a flow store, so that will automatically modify. Sub resource dot mid level is this. Destination sub resource dot mid level is swarm. Mm-hmm. So yeah. This is all like everything from here is the preparation set. For that. For the final thing here. Hmm. Okay, let's step through using the bubble and see what's happening with the math. So destination mid level is 1, mid level is 9, and again. Mid level is 2, mid level is 9, and again. 3, so 4, 5, 6, 7, 8. This is where we need to be careful. Alright? Mid level is 8. It's less than mid levels. That is fine. So far, so good. No errors detected. Run. Step. Did something happen? Nothing happened so far. Okay. Destination width is 1. Destination height is 2. That should not be happening. Something is wrong. Because this is symmetric. Both. Oh, sorry. Destination height is here. Source height is 2 on 2. Destination is 1 on 1. Well, that is correct. They're symmetric, so that's fine. MIP level is 8. Source MIP level is 8. And destination MIP level is now 9. That is obviously wrong. So in reality, what is happening is we need one more MIP level. So if we're going to go down, so that we go down up to 1 pixel, then the floor is wrong. And the ceiling doesn't make sense either, because if you have 4, if the original number is 4, full number, then there are 2 MIP levels. It had 3 total MIP levels because there's 4, 2, and 1. There are 3 MIP levels. So that's log plus 1. So that is 1 plus 4 flow. So here we'll add 1. Alright. Now you should also say this is your WD. And you can run this. Okay, we don't care about you run. Okay, still an issue because base loop level 10 is a thing. That one entirely does not make sense. So let's try it. Again, go there. Net levels is 10, destination level is not 10. So destination level is 2. Source level here will be 1 then, right? So if you look at this, source level was 1, destination level was 2. That was fine. Step, keep stepping until it's 9. Okay, this is fine. The levels is 10, this is 9. Okay, width is 1. The source width is also 1. So that means next step is invalid. Like next step is not a correct step. Lip level 9, lip level 10. Source width and source height, these are all 1s. So now it prepares. Expected. and you run it immediately. That's the error. There you go. Oops. Yeah. So that's the error. What we need to do is we need to move this prepare thing above. Did we run the pipeline barrier before? Yes, we did. We set it up with base map levels and we ran it beforehand. We don't need to. So prepare next map levels are not edited until this point. So in reality, we can move this all the way up there. Because they always do it for the next level, right? So that for the next level as a transfer source. Hold on. Something's not right. Inch. It might probably give us an error at the end. Yeah. Moon layout is destination optimal, but we treated it as if it was a source optimal. There's the order of operations here. It was wrong. The answer is, well, fairly simple. Instead of transfer to ready dependency just being a single thing, we will manually add another barrier in there. So transfer to ready barrier, there we go. Make it 2. So std array of transfer, well, that's a dependency. Or transfer to ready image barriers. It's an array of these things. And that goes away. Pasted there. It's sealed. Okay, now sub-resource range is no longer accurate. So we need to modify the sub-resource range here. What is happening is we're converting it to optimals, but this one should be a destination optimal. Since the last one is left as a destination, we never change it to source. Sub-resource range, these are not going to work out because level count is mid levels on this sub-resource. So we'll have to manually adjust that. As for ready image barriers, yeah, let's do it here. Aspect class, we can manage aspect color bit. Base mid level is 0. Level count is get levels -1. You have to skip the last one. Array layer and array layer count. Okay, that's it. We copy this whole thing and we replace this with that. One small change will occur here, which is mip level will be mip levels -1. Mip level count will be exactly 1. And this should fix our little issue. Yeah, of course. Transfer to image barriers, data. Transfer to image barriers, size, starting cost, and action handle itself. Build, rigor solution. Done. Okay, no errors. Now, as you can see here, it's still not solving that issue. This probably wasn't a Mipmapping issue at all then. Or our shaders aren't doing things that they should be doing. Sample level. Level 0. So that is level 0, but probably not the right thing to do because we won't be able to really test out the difference. So the best way to do that is to check for the interpolated color location, not color. We want the interpolated position actually. So let's get that over as well. Related position. There we go. And if position dot x greater than 0, return this. Else return sample without the leveling. A build solution. And let SDM3, of course, because we just compiled the shader. Okay, can we see a difference between the two? I ought to actually. So the old, I hate this thing. So the old version is on the left side, the new version is on the right side. Okay, that is there. Let's remove the phase change because it's making it a bit difficult to notice the difference. So transform. There we go. This phase difference is making it difficult, so we're just gonna zero it out. Because if it's 0, then we don't need the rest either. And the rebuild solution. Run. Do we see much of a difference? If you notice carefully, not much actually. Yeah. Don't know what to say about this. So check what Mipmapping does. Take out risk mono textures to improve screen image quality. Blah blah blah. You can check this. Aliasing effect because of oversampling, increased performance because build rebuild solution. What we can try to do is fix the sample level to level 5. You will see the difference. Of course. Yeah, good build. Okay, that tells me that the thing is not using mid levels at all. Maybe make it mid level 10, right? 9. It's not 1 pixel, but it's as close to 1 pixel as possible. So this should not give us the same clarity at all. So if it's giving us the same clarity, it's not using MIPS at all. So we go back to image creation, image view, create info, there we go. And we can check what's happening here, right? The mid level is fine. That's image create info, that's view create info. Component mapping is fine. Sub-resource range is okay. Format is okay. Cellularity, there we go. Max NOD What's the maximum value of max error anyway? Let's search. Yeah, copy the wrong thing. I did. Okay, sample period info. Max LOD. So min LOD is to clamp it. Clamp none to allow whatever we want. There we go. Build. That was my bad. And run. Okay, now you can see a bit of a difference. There's no shimmer in either of these images. But clearly it's not actually sample leveling it. Let's check what a sample level does, right? Here I can check it in HLSL because Slang mostly tries to do the similar thing. So sample level is similar to the sample. You choose the Mipmap sample. 2D, it uses this. We just say, okay, choose exactly sample level 0. Build, rebuild, and 12. It's not doing it, but you can notice that there's no shimmer in this anymore. Perhaps it's just this. I don't even know what the X is here. So what I will do is I will say interpolated colors will be replaced by interpolated. Not that. So what I'll do is float for out color. Out was this out color equals that out color multiplied by interpolate it position.x return it dot a. We just multiply by a, multiply the alpha by that. The alpha will be not worth actually. So we can multiply the whole thing and we return the out color. All right. So what's going to happen here is rebuild. What's going to happen here is we just come to less than 0. We use the left side of that. And clearly, that's not it. So interpolate position is not the best of ideas. What next? So instead of interpolate position, we can say float for world position. Actually, screen position is screen position. We have to assign screen position somehow. We will do it from here. Out position becomes screen position, and we'll just assign the exact same value for now. Interact. What's wrong with it? Yes. Load or interpolate position is screen position. Got it. I need to fix that at some point. Okay. There's always some amount of issues with this. Now we can see that the left side is x less than 0, clearly. So we can remove this out color flagging here and run STL. Rebuild solution again. And we do that. And now we can see the left side versus the right side, right? So the left side doesn't use Mipmapping, the right side uses Mipmapping. And while you can see that the left side is crisper than the right side is a little blurry. That's mostly because of the MIP bias, let's say. We are assuming that this level of blurriness is okay at this given level. Sometimes that is not true. And so you change the MIP load bias. It's available as a thing in the sampler. So if we go to the mesh, so the mesh data, CPP, and you look at this MIP load bias, you can actually bias it so that, it changes in a way that's better for you. That it will show the right value. So you can make it sharper. You can say, okay, this level of aliasing is fine with me, but I need the crispness. So compute the bias with a different offset, right? But that's it for now. So you've got mip-mapped objects. It's the end of today's stream, I suppose. This was fun. If I'm going to stream again, I might actually do it today itself, another stream. But we'll see about that. Enjoy, everyone. See you.